Hello all, welcome to this tutorial session in which now we will be understanding an alternative view of DDPM as a regression over added noise. Okay, so now without any further ado, let's directly start looking into the code. In the previous tutorial, we have already looked into the unit architecture, and then we have looked at the way in which the training is being done and the inference process. Now, there will be a very minimal change whenever we are looking at alternative interpretations of DDPM. Now, the first one that we shall be looking is DDPM as a regression over noise. Let's directly start with the code and then we will be going back and forth. Now, the current code that you are seeing is not actually run on Colab. Now, because of some faster requirement, I just ran it on a server. The same thing can work in Colab. You just need to change the CUDA device here just to CUDA CUDA. You have to remove this one there. Okay. So the same thing will work. So I'll be just taking you through the code. The structure that is there in this code is a bit different than the structure that we saw in the vanilla version of DDPM, which estimates the image point itself. Okay, so let's go ahead with that. Now, these are the necessary libraries which are similar. Now, rather than going through the function one after another, let's start with the implementation. And then whenever there is a function call, now we will come and look at each of these functions. I have written this code with a lot of comments so that you can take it as a backbone and then use it for implementation of other alternative views like the mean prediction as well as the score prediction with minimal modification. So let's start with the training process itself. Now the image size that I'll be taking is 32. The batch size is 128. I'm running it for 25 epochs. Now if you want sharper images, now try to do it with more number of epochs. And then the learning rate I have taken is 10 to the power of minus 3. You can chuck by increasing or decreasing the learning rate. And then the time steps that I have taken is 600. So for crisper images, you can try it on increased time steps. The first thing that I'll be taking is the betas. Okay. Now betas is a modified version of alphas. Now alphas is 1 minus betas. Okay. Now in our theory, we only look at alphas. We don't look at betas. In a similar manner, we have implemented earlier. Now it will go and call a function called as linear beta schedule. Now for this you are giving time steps 600. Let's go back to that linear beta schedule. Now it is giving you from the starting point, okay, which is 0.0001, which is 10 to the power of minus 4 till 0.02. It is giving you an equi-spaced 600 instances. Okay. So this is what this function does. So now we will come here and then we will get 1 minus alpha. That is what we wanted. We wanted my alphas to be greater than 0.99. Okay. So and then you have cumulated alpha now, which is at a given point, you cumulate it like alpha 1 into alpha 2 into alpha 3. You get that. Okay. And then now this is at a point t, you would have accumulated all till t. Now this is accumulated previous. Now this is cumulation till t minus 1. And here you have square root of the alpha accumulated. Okay. And then this is square root of 1 minus alpha accumulated. Now why do you need all these things? Now as you can see here, now these constants are needed in obtaining our equations, in obtaining the points. Okay. Now rather than doing it then and there, now we prepare a list now wherein which all these points are readily available to us. Now this is square root of alpha accumulated product. Now this is square root of 1 minus alpha accumulated. Okay, yeah. So now uh, then we will look into the posterior uh, variance. Okay, and then similarly you will get the variance of it. So we are using MNIST data. Now you are transforming it, and then you are obtaining the data loaders, and then you are calling the model which is unit. Okay, now let's look at this unit architecture. Now this unit architecture, now it is having the image channels as 1. Since I am working with MNIST, the initial the channels that you have is 1, and then the down channels. Now you might be remembering. Now the down channels is 64, 128, 256, and then the up channels now that you have is 256, 128, and 64. Now to this, now please remember that now there will be a residual path that is there which needs to be taken care, and the output dimension is 1. Okay, now unlike the segmentation problem in which we had an output dimension of 3, now here output dimension is 1. The time embedding dimension now that you are having is 32. Okay, so and then first what do? You obtain a sinusoidal embedding. Now let's go back to the sinusoidal embedding class. Okay, now once it is called, now you are calling it from here, from the embedding dimension, which is 32. Now as you might remember, now sir in his theory sessions has explained how do you obtain the sinusoidal positional embedding. Okay, I'll not be going ahead into the theory aspect of it. It is exactly the same formula now which is being implemented here. So and then after that, after you have obtained, there is a learnable layer, an MLP layer from the time dimension, time embedding dimension to the time embedding dimension. Now so that the parameters are learnable, because of which you get better holding on the positional encodings. Now, and then you have the first layer where which image channels which is 1 to 64. Now down channels of 0 is 64. The kernel size is 3 and the padding is 1. So since you have not provided the stride, which means that the stride will be 1. Okay, and then you have the downs now wherein which you see there is an increase in the number of features, and there is a decrease in the spatial dimension of each feature. Now it is doing an operation called as list comprehension. The way in which it happens is, now this operation is called for each I here. Okay, so now let's look into it. Now there is a block here. Now first down channels minus 1. So the length of down channels is 3. So now it is 2. So the first value that I get is 0. So I'm calling a function, I'm calling a class block of down channels of 0, which is 64, 128. Okay, now let's go back to this block. Now what is it doing here? Here is the block. Now it takes in channels, out channels, time embedding dimension. Okay, now as you can see here, the 64, 128, and then 32. Now this is what you have got. Now here you see an initialization. Okay, now first you are having an learnable parameters for the time MLP. Now from the 32 to whatever is the out channel. Here the out channel was 128. Now so that now you get a vector of size 128 that you added into the each of the features plane is what the positional embedding actually means. So now if it is an upsampling process, okay, now you have transposed convolution. Now if it is a downsampling process, now you have just the convolutions with you. So followed by a batch normalization and then the ReLU activation. Now this is the forward process of it. Now first you pass through the con1. Now if it is an upsampling, or the downsampling, or depending on that. Okay. Now if it is an upsampling, the input channels is 2 times of that. Now because you will be having a residual connection, a skip connection, which is there, which is coming from the encoder part in the unit. So because of which the in channel will be twice of it. Okay, so and then you will, after that you will be having a transposed convolution to out. Okay, yeah, now this is a different way of writing a unit architecture. Now we wrote it in a straightforward manner. Now this is like you have multiple function calls to take care of it. Okay, now you have passed through convolution one, and then after that you pass through the normalization, then you have ReLU, and then you obtain the time embedding, and then you pass it through ReLU. Okay. And then what do? You reshape this. Okay. Now this is a vector which is of size b comma out channel. Now what do? You reshape it now so that you can add it to the output of the ReLU here. Now then you add it, then you pass through the next convolution layer, batch normalize it, ReLU it, and then you send it out. Okay. Now this is regarding the block. Now if it is an up convolution layer, you'll be having convolution layer and then followed by a transposed convolution. If it is a down convolution, now you will down stream going, now you'll be having a convolution and then followed by a convolution. Okay, so now let's continue with the unit. Now what it will be done? Now 64, 128, 32, it will be the first thing, and then 128, 256, 32. Okay, now you will be having two blocks. Now, similarly, the same thing will be there for the up module. Now here you are sending up is equal to true. Now so that in the block you recognize that now this is a upsampling. You need to decrease the number of features and then you should increase the size of the features, the spatial dimension of the feature, now so that it get back to the image size. Okay, and finally from the last up channels of -1, which is 64, you have to finally put it into the single channel image. Okay, that is what you are doing finally here. Okay, so now then, if how is the forward process looking? Now you get X and then the time step. Okay, so now first you get the MLP, where in which you get the time embedding, and then you pass through the conv 0, now which is this, and then you have residual inputs. Now if you are looking at the down process, okay, now then you have to append all the outcomes of the each of the blocks, now so that you have to connect it to the up convolution again, and then in the up convolution process, okay, now you concatenate X and the residual X is what you are getting from the downstream, and then you pass it through the up convolutions. Okay, now this is the idea of the unit. Okay, now similar to the same idea, I just briefed it out again. You're using an Adam optimizer, and then the loss is MSE loss. Yeah, now you are keeping track to bookmark the loss history so that we can plot the loss curve. Okay, so now let's look at the training process. So now first you take an image X0 and then you take a T. Now you choose a random T from 0 to time steps, now which is 0 to 600, which is of size batch size. Okay, now you have randomly selected a bunch of T's. Okay, now and then you are porting it onto the device, and then you are doing the forward diffusion process. Now let's go to this function, which is forward diffusion, to understand it. Yeah, here is the forward diffusion process. Now wherein which you have to get xt and then the noise. Now please remember, now this is the equation that will be implemented in the forward process. Okay, so now first you get a noise, random noise, now which is the same size as that of the x naught. Okay, which is xt. Now you're sampling from 0 1, you have got this. Okay, this equation is done, and then get index from list. Now what is this? Okay, so now please look at it here. You need for the specific T. Okay, now the way in which this get index from list is implemented is, now you give whichever list that you have, and then you give the T. Now it will give the specific alpha T's that are needed. Okay, so now you get for that specific time point, you have got the square root of alpha accumulated. Now that's what you have got. You have got this now, square root of alpha accumulated product. Okay, and again you have to get this now. That is the next step that you are doing. Now 1 minus square root of alpha accumulated, you are sending the 1 minus alpha accumulated now with the t, and then which is, so you should be getting it as per the shape of the x0, which is your true image. Okay, so now from the equation it is clear that now this is the mean and this is the variance that you should get, and the mean is the square root of alpha cumulative product t into x naught. This is the mean which you have got, and then the variance is now 1 minus square root of alpha accumulated product into noise. This is the thing. If you add them, you get the noisy version of the image at that specific instance t, and then you are sending the noise also. Now this is the forward diffusion process. Now coming back to the training procedure, you have got the xt, the noisy image at that time stamp t, and then the noisy target, and then you get the predicted noise from the model. Okay, as I told you, this is a noise estimation. So you get the predicted noise, you give xt and t, it will be giving you the predicted noise. Okay, and the noise is the same shape as that of the image in all the diffusion process. And then you have the MSE loss from the noise target to the predicted noise. Now this is the target now which I got from the forward diffusion process, and then this is the prediction which I got from the model. I obtained this. Okay, so now this is what you have got. Okay, so this is what you have got, this term. Okay, and then you backward, so you get the gradients and then you update the steps. Okay, now this is the overall training procedure that you do it for one noise. So normally you can include one more a batch here, when which you can include one more step to take care of it. Okay, so this is the overall training process. Now coming to the inference, yeah, you can see the loss curve. I have ran all these things so that I can show you the output results. Now coming to the inference process, now how does the inference happens? Now the inference is exactly similar to the way that we had inference in the sample estimation case. So now let's look at the inference thing. Okay. So now first you get betas, now all these things. So square root of 1 minus, so all of them, all the necessary things you get. Okay. And then you get the predicted noise. Now once you have got the predicted noise, now then you have to obtain the image, now which is mean plus the square root of posterior variance into noise. Okay, now this is what you will be obtaining at every step t. Now that you in a reverse order from reversed order from 600 to 0, you do it, and then at the last step you add 1 and clamp it till 0 1 so that it is in a printable way. And these are the images. So there is an issue. Now the background, as you can see, is not pitch black as you were expecting in a standard MNIST outcomes, which we have got even in our sample estimate. Now just to reiterate, now this is the sample estimation problem. Now the outputs that we have got. Now you can find the notebook of this in my GitHub repository, now which you can make use of it, which is not happening. So I will leave it to you as a simple exercise on train it further, tune the hyperparameters, and see why I am not getting the background. I'm getting the images of the foreground, but my background is not clear. I will leave it to you as a very interesting and then a small exercise so that you will be able to do it. This is where I stop with noise estimation with the same method. Now you can go ahead now with the mean estimation as well as the explicit score estimation. Now if you have estimated the noise, now which is considered as an implicit score estimation, you can similarly do it for external explicit score estimation exactly with the same code with a very minimal modification that is needed. In the coming tutorials, we will be preferably using the same structure, wherein which I'll not be going ahead into the details of how the parameters, not the you should not call it as a parameters, how the terms like alpha and things are fixed, okay, and then how the forward process and how the unit architecture. Now those things remain same for the remaining tutorials that we have in this module in the next tutorial. Okay, those things remain same. Now with this, we conclude the tutorials on noise estimation. We will meet in the next tutorial. Thank you.